Okay, so now we're going to talk about apparent weight because as you can see, whatever we're going around on a circle, in a vertical circle, we've got there's going to be a normal force and there's going to be a force of gravity. If you remember back from when we were talking about elevators, okay, and problems in elevators, we talked about apparent weight then, and that was the weight a person feels. This at that time was the normal force because you don't actually feel gravity pulling you down. What you feel is the force holding you up. So, if we can remove that force completely, you will experience what we call apparent weightlessness. Now, this is a person in free fall. So that means the only acting force is gravity. Therefore, the person doesn't feel any other forces. Now, we really have, there's very few times that we actually experience this. It is important to note that a skydiver would not feel apparent weightlessness. They would not feel weightless. The reason they wouldn't is because they're moving so quickly. They feel the air pushing on their face. They feel that air resistance holding them up. They feel like they have some weight. So they actually would not be weightless in this situation. So if you just watch the video where we went through all of the ball on a strings and Ferris wheels, remember every vertical circle can be broken down. It's either a ball on a string or it's a Ferris wheel. So we're just going to focus on those two. So if we take a look at a ball on a string, at the top of whatever it is, it's going to have a force of gravity down, and there's a tension pulling it down as well. But if we're at apparent weightlessness, all right, that means the only force acting is gravity, meaning that the tension is zero. So there is no tension in that string. We don't feel it, therefore we feel weightless at this point. So I'm just going to get rid of it. So I'm just going to erase it all. So the tension is gone. That means the only force that we feel, or excuse me, the only force that we experience is gravity, and we don't feel it. Therefore, this is apparent weightlessness. Now, let's take a look at what happens here. We know that the centripetal force is equal to the sum of all the forces. Well, in this case, the centripetal force is equal to the force of gravity. We also know that the centripetal force is the mass times the centripetal acceleration, and the force of gravity is mass times gravity, which, hey, if you look at that, this turns into a nice massless problem because my masses cancel. And so the centripetal acceleration equals gravity. Now, that means that V squared over R equals 9.8. All right. So all we have to do now is figure out how fast we're going or how big the circle is or something like that. And we can actually create weightlessness for any object. This is why on a really good roller coaster, there are times when you feel like you are floating in your chair. And this is because they have calculated the velocity to create apparent weightlessness. And you don't have to get on a scale before you get in a roller coaster. So this does not depend on your mass. All it depends on is how big the circle is. And for that circle, so for that radius, there is a velocity that creates weightlessness. And that, on a ball and a string, is when that tension or that second downwards force equals zero at the top of the circle. Now let's go over and look at a Ferris wheel. Now if we go look at a Ferris wheel, we have a force of gravity down. Okay, but the normal force is usually up. Again, the force we feel is the normal force. So if we remove the normal force, just get rid of it completely. Now we feel weightless because we're not able to feel gravity. Again, if we take a look here, we know that Fc is equal to the sum of all the forces. Well, that is just Fg again. And so we get the exact same thing. The masses cancel. And we get the centripetal acceleration is equal to G, or M, excuse me, sorry, that was a typo, or V squared over R is equal to 9.8 again. All right, so again, if we know the radius of the Ferris wheel that we're sitting on, then it's just a matter of running it through this quick calculation to figure out how fast you have to go in order to make the person feel weightless. Now, for each of these scenarios, it's a little bit different because if we talk about, sorry, lost you there for a second. It's a little bit different. If we talk about what happens when we're talking on a ball and string, this velocity is special. So let's talk to ourselves what happens here. If we go faster than this weightless velocity, this velocity that creates this apparent weightlessness, what happens? Well, what ends up happening is that this relationship is no longer true. If velocity increases and we keep the radius the same, the only thing that is possible here is that this number on the right side of the equation has to go up. If that's the case, then the centripetal force is greater than gravity, and so then that tension comes back and we end up with a tension. Okay? So what that means is the weightless velocity is the smallest velocity possible for a ball on a string to continue in a circle. If you go slower than that weightless velocity, what ends up happening is that the object doesn't have enough inertia to maintain that circular motion. And what will happen is it'll continue to move in a circle. It will just move into a smaller radius. So for a ball on a string, it's very important that you realize this is a minimum. You must go at least that fast in order to maintain your velocity. Now, if we take a look at the Ferris wheel, all right, if we take a look here and we start thinking about, okay, what happens if we go faster? What happens if we go slower? Well, if we go slower, there's no big deal there, right? If we go slower, what ends up happening is that the person in there has less inertia and will actually press against the seat a little bit, and the normal force comes back. All right. So if we go slower, no big deal. We just have a normal force because at this point in the Ferris wheel, there's something sitting underneath us to hold us up. However, if we go too fast, what happens? If we go too fast, if we increase this velocity, what ends up happening is our centripetal acceleration that we need goes up. This would go up. Unfortunately, all we have is gravity. We don't have another force available to us to apply a force down to compensate for that extra needed acceleration. So what happens if you go faster than the weightless velocity? What ends up happening is whoever is sitting here in the Ferris wheel, they become a projectile. This is bad for repeat business. So the Ferris wheel operator will likely take you close to, on a very nice Ferris wheel, will take you close to the weightless velocity, but will not actually hit it. Because if he goes a little bit too fast, you go launching, flying off of there. So very important to realize that on a Ferris wheel, this is a maximum. You cannot go faster than this. If you go faster than this, like I said, the object just simply becomes a projectile. Now, so what we've learned so far is that in both a ball and a string and a Ferris wheel, so all vertical circles can have a weightless velocity, a moment when the object feels weightless, as long as we hit the certain velocity. If we know the radius of the circle, we know exactly how fast it is, and we can create weightlessness. Now, at the bottom of the circle, is it possible to be weightless at the bottom of the circle? The answer is no, it's not. And here's why. Because it doesn't matter the bottom of the circle, they look the exact same. There's a force of gravity down, which we don't feel. But on a ball and a string, there is a tension up, and that tension must be bigger than the force of gravity. So we have to feel the force at the bottom. On a Ferris wheel, it's the normal force. We have to feel that force. We have to have that acceleration up. So either way, this at the bottom of the circle, we cannot feel weightless. It is not possible. However, something is true and unique about both things. So now this is true for both of them. So I'm just going to do it once here in the middle. We know that the centripetal force is equal to the force of gravity. This is true because we're still going the same velocity as we were at the top, because it's uniform circular motion we're talking about here. So again, this would be mass equals a, oops, sorry, I'm going the wrong way here. I'm going to erase this. We know that that has to be true. Well, here's the thing. Now, gravity at the bottom of the circle is negative for both of these things. All right. Now, the centripetal force has to be equal to one force of gravity. That's from the top. So, but the centripetal force is also equal to the force of gravity plus the tension or the normal force. I'm just going to use tension because it's a little simpler to write. But we know this is what it's equal to. All right? So we know that Fg is equal to the value of Fg, but now it's negative. So it's negative Fg plus whatever the tension has to be. So if we solve for this tension, or like I said, easily we could plug in F norm there, would be the exact same thing. If we solve for the tension, well, if we just add Fg over, add Fg, at the bottom, that upwards force, so a tension on a ball and a string, is equal to 2 times the force of gravity. On a Ferris wheel, this tension would obviously be the normal force. So, there are two very true things at this velocity. At the top of the circle, if it's a person, they will feel weightless. For a ball and a string, that's the minimum velocity to maintain uniform circular motion. For a Ferris wheel, that is the maximum velocity because we actually have some support under it. We can go slower than that on a Ferris wheel. At the bottom of either one, it